So the next part of this is factoring quadratic expressions with a greatest common factor. So the first rule of factoring really is just look for a GCF, because if there is a GCF, you need to factor that out first, and that will usually make the rest of your factoring easier. As I look at each expression, a greatest common factor means that you're analyzing each term to see what is in common in each one. So if I have a 3n squared, an 18n, and a 48, there's a greatest common factor, a number that divides into all of them, which would be 3. A greatest common factor can be a common number factor, but it could also be a common variable factor that we'll see here later on. So what we're going to do is just undistribute that 3 out of every term. So that undistributing is really just dividing a 3 out of everything. And so if I took 3n squared and divided it by 3, I'd be just left with n squared. If you have negative 18n and you divide by 3, you're left with negative 6n. And negative 48 divided by 3 is a negative 16. So we talk about that as an undistributing process, because if you went back through and distributed, you would get what you originally started with. So you can check your answer just by thinking 3 times n is 3n squared. 3 times 6n be negative 18n. 3 times 16, negative 48. And that's what we originally started with. So now we have undistributed, and that is our GCF. The GCF is just a multiplier to the rest of the expression, and so it's going to kind of hang out front while we worry about this quadratic expression that's left. So here we have another quadratic expression that we're trying to continue factoring. By factoring out the GCF, it's making this next part easier, because now our quadratic term is just an n squared, which would have multiplied or came from multiplying n times n. Then we skip back over that middle term, that linear term, and go to the constant term. And we find, what are some factors of 16? Well, you could do 4 and 4, or you could try 8 and 2. And I'm going to just jump to 8 and 2 because it will work. In the previous video, we talked about just this guess and check method, but part of it is just checking the insides and outsides of that quadratic factoring. So the inside would be 8n, the outside part is 2n, which does combine to give me a negative 6n if that was a negative 8 and a positive 2. So if I had n minus 8 and n plus 2, we can just double check it, but n times n is the n squared. We already know that the 2n and negative 8n combine to give me the negative 6n, and the negative 8 times 2 is a negative 16. So this did factor. I can erase this checking that we did. But this would have factored into 3 times n minus 8 times n plus 2. That 3 is important. So if we're looking to factor it completely, 3 times n minus 8 times n plus 2 is completely factored. Without the 3, it would never have multiplied all the way again back to the original 3n squared minus 18n minus 48. So our final answer just is all 3 factors. One just happens to be a constant term, which is that GCF. All right, in this next one, it's actually not quadratic at all. And we have an n to the third power, so it's a cubic expression. But we still always look for a GCF. So a GCF here, I'm looking at the 5n cubed, the negative 15n squared, and the 50n. One thing I notice is that every single one of them has a factor of n in it. So part of the greatest common factor is going to be n. But if I look at the coefficients, 5, 15, and 50, all of those also are divisible by 5. So 5n is the GCF. What we're going to do is undistribute the 5n out of every term. So you're dividing each term by 5n. If you think about 5n cubed and you divide out a 5n, 5n cubed is just 5n times n. You're dividing a 5n. So 5 divided by 5 is 1. N divided by n is just 1. So we are left with an n squared. Then we divide here again. Negative 15n squared divided by 5n would be a negative 3n. And negative 50n divided by 5n would be negative 10. Again, you could go back through and redistribute to check your answer to see that it does give you back what you started with. And it does, so we know we're good there. What we now want to do is try to factor the rest of that quadratic expression. So we did end up with a quadratic expression that can factor further, but we have this GCF here. Now, a common mistake I'll see is that students will just jump straight into this factoring, but forget that there's a GCF that's also part of the factoring. So you want to make sure that you're bringing down that GCF. We jump back into the guess and check method. So n squared came from n times n. And we find what things multiplied to give you a 10. This could be 5 times 2. If we check our work, we get 5n on the inside, a 2n on the outside. So negative 5 and a positive 2 would combine to give me a negative 3n, which is what we needed. I need a negative 5 and a positive 2. Again, double check because we want to make sure that negative 5 times 2 is the negative 10 that we want. So just check your signs to make sure that you've got it correct. This is completely factored now. You don't really need the checking part of it. So our final answer in completely factored form is just this part here. So you could just write it again if you want to, but 5n, n minus 5, n plus 2. Alright, if we skip to 3, negative 2b cubed plus 6b squared minus 4b. One thing I see already is that there's a b in every term. So at least, at minimum, there's a GCF of b. But a trick that I would encourage you to do is just to always, if there's a negative as the beginning coefficient, is to also factor that out as well. So I do see that 2, 6, and 4 are all divisible by 2. So I could say the GCF is 2b. But since that's a negative in the very beginning, I'm going to factor out a negative 2b. That makes this beginning term b squared. And that's going to be a lot easier to factor than if it was a negative b squared. But if you are factoring out that GCF, which was negative 2b, then that 6b squared divided by negative 2b is going to be a negative 3b. And negative 4 divided by negative 2 would be a positive 2. B divided by b is just 1, so we do end up with a positive 2 on the end. It has changed the signs when you factored out the negative. This does make that easier because now that quadratic term is a positive b squared. And we're looking to see b squared came from multiplying b times b. There's only one way to get a 2. It's 2 times 1. But we need a negative 3b, and we'll see that when we check this, negative 2b and a negative 1b, kind of got ahead of myself, But negative 2 and negative 1 would make that negative 3b, so I do need both signs to be negative. If they are both negative, negative 2 times negative 1 is a positive 2. All right, so our final answer in completely factored form is what we have there at bottom, but I'll just rewrite it one more time. So negative 2b, b minus 2, b minus 1. All right, and this fourth one, there's only two terms here. But again, the first rule of factoring is always to look for a GCF. So if I've got a 6 and a 48, something that divides evenly into both would be 6. But I also have an x cubed and an x squared. Now the greatest common factor is looking at how many of the factors are in common, and that's not as obvious, I guess, when it's written out like that. So I'm just going to expand it for a moment just so you can see that there's actually two x's that are in common. X cubed is made up of x times x times x, x squared is x times x, so I could pull out a 6x squared as the greatest common factor and be left with an x plus 8. Now that x plus 8 would not continue to factor. So this is all I can do, is just pulling out that greatest common factor there. There's no continuing because that's not a quadratic expression there. Alright, so here are a couple for you to try on your own. So if you'll pause the video, and then you can check your work after you are completed with these 4 questions. Alright, so if I pulled out a GCF, it was a 3. So that would leave me with a 2n squared, a 4n, and 90 divided by 3 is 30. Actually, what I see now is that 3 was not the greatest common factor, it was 6. Because 2, 4, and 30 also have a greatest common factor of 2. So that means I didn't pull out the biggest common factor. That's one way to kind of check your stuff there. So 6 would be the largest, and that would mean I have n squared plus 2n minus 15. And we continue factoring. That would have been 6n plus 5, n minus 3. Alright, in number 6, your GCF is 5b. We're left with b squared plus 4b minus, let's see, that would be 60. Alright, and 5b plus 10 minus 6. Alright, in 7, you have a GCF of 2k. Plus minus 7k plus 10. So 2k times k minus 5 times k minus 2. For number 8, you would bring out a 2n squared and be left with n minus 8. And that doesn't continue to factor, so that's all you can do for that one. Now I do have 2 more for you to try, so if you want to pause the video again, you can try these on your own, or if you just want to do them with me, that is fine as well. Again with number 9, because when I look at this, there doesn't seem to be a GCF. There's not an n in common with all of them. And there's no number that divides evenly into all, but there's that negative in front. So actually I want to pull out a -1 and make that n squared plus n minus 56. And now that's going to be easier to factor. So that could be n plus 8, n minus 7. If you want to double check that, you would start here in the beginning or with n plus 8, n minus 7. That gives me 8n, negative 7n, combines to give me a positive 1n, which is what we needed now, because I'm factoring this expression. It does multiply to give me a negative 56, because positive 8 and negative 7 would be negative 56. When you distribute the -1 from the GCF, it will give you the original quadratic expression. So that's our final answer, just -1, n plus 8, n minus 7. And you might not see the -1 there. It might just say negative, and then an n plus 8, n minus 7. That's also acceptable. It's implied that there's a 1 there. I typically like putting the -1 just to kind of serve as a reminder that that's not just some random negative. It has a purpose from the GCF. All right, and number 10, we have a GCF of 4. $324 divided by 4 is 81. This actually continues to factor. So I know there's no GCF here, x squared minus 81. I've pulled out the biggest common factor. But it does continue to factor because I can get an x squared from multiplying x times x. We can get an 81 by multiplying 9 times 9. And there's a 0x term here right in the middle that's kind of missing. That's because if I had a positive 9 and a negative 9, they would combine 9x and negative 9x to be 0x. So this is actually completely factored. That's because that x squared minus 81 was a difference of squares, which we talked about in the other video. I'll do a whole video just on these in case you need it.